So now that you know a little bit more about the concept of lambda expressions and method references, let's take a bigger view of how these things get used within the Java class libraries. And this will be something called functional interfaces. Now, as you'll see in a second, there's lots of functional interfaces. We're going to focus on 5 of the most common types. And not only are these just very common, but they're also the core functional interfaces that are used with streams, both sequential streams and parallel streams, as well as with completable futures. So understanding these 5 types of functional interfaces will make life much easier as we go further along. And that's why I was saying here, they're the foundation for the parallelism frameworks and concurrency frameworks and so on. I'll show you a bunch of examples. All of these examples will be available here in my GitHub repository. And if you have any questions about how they work and want to see more details than what we can cover on the slides, please take a look at them. They're really meant to be short and to the point. They're commented, so you should have no problem figuring out what's going on. All right, so what the heck is a functional interface? I'm going to give you a definition here, and it's a pretty good definition, although you'll see by the time we get to the very end, there's a slight quirk with this definition for certain very, very foundational Java classes like java.lang.object. But ignore that for the moment. So for the time being, a functional interface is simply an interface that contains only one abstract method. And there's plenty of good examples of these that you may already have worked with. In fact, I've shown you one already. So the stuff we talked about earlier when we discussed the simple example where I spawned a thread and printed hello world, that used the runnable functional interface, which has a single method called run that takes no parameters and in that case doesn't return a value. There's also another popular functional interface, which we'll talk about later, called callable, which takes no parameters and returns a value of type v. So those are both good, clean examples of functional interfaces. We use functional interfaces as the types when we want to pass parameters to a method where we expect to be passing a lambda expression or a method reference as the actual argument. So we use these things to pass information around. And you'll see why we do this in a second. But here's just a simple example to make the whole point more concrete. So if you were to take a look at the ex16 folder in my Java 8 folder in my GitHub repository, you would see there was a method called run test. And just at a higher level, this particular example is cool because it shows like 4 or 5 different ways of computing factorials using different techniques, parallel techniques, sequential techniques, arbitrary precision techniques, built-in long techniques, and so on and so forth. And so what I want to be able to do is I want to have one generic function called run test where I can essentially pass all the different types of factorial computation methods as parameters so I can test out the different things and do an apple-to-apples comparison. So it's easy to see which one runs better and runs more scalably and computes the right values and so on and so forth. So to do this, to make this nice and generic, I make run test a function that's parameterized by type t, where t is whatever I'm going to be working on, be it a long or a big integer or whatnot. And then I'm also able to pass in different kinds of factorial computation methods. So you can see here when I call run test, in this particular case, I'm passing in the parallel stream factorial : factorial method reference. And it may come as no surprise, I also have a sequential factorial method, and so on. So I can pass those different methods in easily without having to change the way my run test method is set up. And my run test method does a bunch of things. I'm just showing a little snippet of it. But basically what it's doing is it's taking a function, which I call fact. So fact is just the name I give to a function that maps a t to a t, and I'll talk more about that in a second, and a value n, and I'm calling a function called apply on fact, giving it the value n, and then it's going to return the nth factorial. And what's cool about this is it allows me to be able to pass in different factorial implementations and reuse that same piece of code up there. OK, so here's just a snippet of the parallel stream factorial : factorial method implementation, for which the code in red here is the method reference. And as you can see here, this is kind of getting ahead of ourselves a little bit, but I just want to show kind of what it does under the hood. This factorial implementation is going to work on big integers, so that means we can do arbitrary precision factorials, which is good because factorial grows very quickly, as you know. And what we're going to do here is we're going to create a stream of values from 1 to n. We're going to run everything in parallel. We're going to convert each of these longs into a big integer, and then we're going to go ahead and do a reduction. So we're going to multiply all the big integers that occur in the stream together in a tree-like fashion until we end up with a single reduced result, which will be n factorial. And we give it an initial value of 1, because multiplication works nicely with the ability to have an identity function of 1. So that's just illustrating how we can compute a parallel factorial. We'll talk more about that later. The main point here, though, is I can pass this parameter as a function. This method reference can be passed as a function to the run test method. And that's what a functional interface is used for, to pass these things as parameters. There are lots and lots and lots of functional interfaces in Java. So as you can see here, there's these by consumer, by function, by predicate, consumer, function, and so on and so forth. Lots and lots of stuff. And then there's also, believe it or not, even more things, because not only do they have the reference types, which are the ones like this, they also have primitive type function interfaces for int consumer, long function, double consumer, and so on and so forth. So there's lots and lots, dozens and dozens of these things, scores of these predefined functional interfaces. And that's, again, a little bit of a quirk of Java. Java has 2 type systems, one for reference types, that are classes, and one for primitive types, which are things like long and int, and so on. We're just going to focus on the most common types of functional interfaces. Notice how in all the examples I'm about to show you, we're using the functional interfaces in a way that leads to stateless computations. So we're not going to have side effects. Remember I mentioned before how side effects are the root of all evil in parallel computing. And so we're going to avoid using them by making sure that the functional interfaces don't have side effects. They just do computations within the function itself. OK. So let's start with a really, really, really simple functional interface. This is the most basic one. It's called predicate. And a predicate is simply a piece of code, a computation that performs a test that returns true or false. So it's a predicate. And here's the interface, the functional interface for predicate. You can see it has a single method. That method is abstract. And the reason we know it's abstract is because it doesn't say static. So it's an abstract method by default. And that's the method. You can see that it simply takes a variable of type, or a parameter of type t, and returns a boolean. So it has a single parameter. It's a single parameter generic interface called predicate. So let's take a look at a very simple example to illustrate how this works. So I'm going to go ahead and make myself a map. It's going to map string to integer. And I'm going to implement this map with a concurrent hash map. It's kind of overkill for this simple example, but just to illustrate how you might do this. So we can make ourselves a concurrent hash map. And then we're going to go ahead and initialize that concurrent hash map to have 3 names, Larry, Curly, and Moe, which are our good friends, the 3 Stooges. And we're going to take a rough guess at what their IQs are. And they're probably rather low, because they're Stooges after all, right? They're the 3 Stooges. So this is a Stooge map, I guess you could call it, or an IQ map, as I call it here. So that's just kind of setting things up. Any questions about that? Does anybody know what a concurrent hash map is, by any chance? Does anybody know what a hash map is? Yeah. Right, so map is essentially a way of mapping or associating a key with a value. So in this case, the key would be the string, like the Stooge name, and the value would be the Stooge IQ. So we have name and IQ, which is string and integer. So that's just what a map is. All a concurrent hash map is a map that lets you do operations on the map from multiple threads of control without corrupting the map's internal data structure and without giving you inconsistent results. We'll talk more about that later. OK, so that's basically what we're doing here. And then we're going to print some stuff, and we're going to do some operations on the map. And you can take a look here. This is the example that this code comes from. So I'm going to call a method on concurrent hash map called removeif. And removeif is going to delete entries with, it's going to delete any entry where the IQ, where the value is less than or equal to 100. So if we print out the map here, we're going to get Larry, Curly, and Mo. If we call removeif, then we're going to remove any entry whose value is less than or equal to 100. So poor Curly and Larry are going to go away, and we'll just be left with Mo when we're all done. And then when we print the results out, they'll be different. I mean, there won't be those entries in the map. Note, by the way, that this use of entry here is shorthand for open paren, entry set, string, integer, entry, close paren. So this is leveraging those type inference capabilities I mentioned before, where Java 8 compiler can figure out, aha, this thing must actually be that thing. And the only reason I show you this is just get used to reading it like that, because that's how everybody writes the code. Very few people, if anyone, would ever write code that looked like this. Although it can sometimes be helpful to know what the actual types are, to know what you can do with the value you've got here. And so if you're ever curious and you're using a modern IDE like IntelliJ or Android Studio or whatnot, you can actually put your mouse over this and it'll give you the option of being able to convert it back and forth from this concise format to that more verbose format that has the type information embedded. So it's kind of easy to go back and forth and see what's going on. Yeah? So you're asking what happens if two threads were to simultaneously do this?
No. What happens? Let's say we have two.
Sorry, I don't quite understand what the issue.
Let's say we have three items. Could also be both sets.
I'm not sure I understand your question, but maybe I can, when I show you how this code works, it'll help make it more clear. This is just the name that we're using syntactically so we can refer to each element, or actually, so this removeif element can refer to each of these elements as it does the operations to check to see if something should be removed. So we could call this foo for all it matters, and it would work perfectly fine. You just say foo, and then you say foo.getValue. So this is just a name that's used within the lambda expression to refer to what it is we're trying to access. Yeah?
Can you print out?
It'll print the key and the value. Yeah, that's a great question. So the question was, what happens if you print the values? Some of these things, just to make the examples more concise, I leave out some details. But if you go and run the code, you'll see exactly what it prints out. That's a good question. So what we're trying to do here is we're trying to give a lambda expression that indicates to the removeif method what we want removed from the map. And I'll go through this in more detail. It may help answer some of your questions. All right. So the interesting thing here is, this is from the caller's point of view. This is what removeif is doing from the point of view of the code that's calling the function and passing in the lambda expression. Let's now go take a look at what's going on under the hood in the implementation of removeif. So if you were to go and look at the collection interface, if you were to look at the source code for Java, I think I gave you the URL to find that source code earlier, you would find this fragment of code. I'm only showing you a piece of it. There's a method called removeif that's actually part of the collection interface. Note something really interesting. In previous versions of Java, interfaces could only define method signatures, but not method implementations. With Java 8, you can now give default implementations of methods in an interface. So when we say default here, what that's saying is unless somebody does something else to override this method, this is the default implementation you'll get. There's a whole bunch of reasons for doing this. It really cleans up library design and maintenance in Java in going forward from Java 8. So here's what happens. Removeif is a method. You can see it's passed in a predicate, and it has this question mark super E. All this says is that whatever E is, whatever the type of the collection is going to be, this thing needs to be an an E or a subclass of E. That's what that funky question mark syntax means. It just means it has to be, whatever this thing is, it's a subclass of E or E itself. So we have this thing called a filter. And what we're going to do here is we're going to use this filter to test each element in the collection. And if it matches, we're going to remove it. So this is what's called a predicate operation, removeif. So if the filter matches, remove the item, otherwise don't remove it. So as you can see here, that's the lambda expression that's actually passed in as the filter predicate, entry.getValue less than or equal to 100. That's the lambda expression that's bound to this particular variable, which is a parameter. And then here's where this actually gets used. So if filter.test each.next, because it's basically, notice how it's iterating through every element in the collection. If there's a match, we're going to remove the match. And what this code here effectively turns into is something that looks like this. If each.next.getValue less than or equal to 100, then remove the item. So that's the actual binding that's going to be happening at runtime when we pass in this lambda expression to the removeif method. Did that help answer your question from before, or do you still have a question about that? Okay, great. So what we're doing is we're basically, this is effectively what's happening. It's as if we're replacing filter.test with the code that's passed in as the lambda. Question? Very good question. So the question is, the basic question is, what's the difference between an interface and a class? So for a long time, up to Java 8, it was really easy to explain the difference between an interface and a class in Java, because an interface could really only define, effectively, method signatures, could not define implementations. So that was an easy differentiation, right? With modern Java 8, or Java 8 and beyond, all of a sudden you can have these default methods in class. Well, there's some things that you can't have in an interface that you can't have in a class. For example, you can't have non-static fields in an interface, whereas you can have non-static fields in a class. So they're gradually becoming more like each other, but they're not quite equivalent at that point. And that's one of the main differences, is you can't have non-static fields in an interface, even with Java 8 and beyond. Okay, so that was basically predicate. Very simple. You will actually get a chance to use predicates as we get further along in the course when we start doing streams programming, because it turns out that there's an operation that works on a stream called filter, and you give it predicates, and it basically filters out stuff that, it filters out things that don't match the predicate. Okay, next functional interface, function. This is ever so different from a predicate. So if you recall predicate, it took a single parameter and returned boolean. Function, in contrast, takes two parameters, t and r. Those are type parameters. And it's implemented with an apply method, not a test method. And what it does is it applies some piece of code on parameter of type t, and it returns something of parameter type r. So it's basically the kind of the textbook definition of a function, right? It takes a parameter, applies it, and then returns a result. So t and r are just the types of the parameter and the return value. Here's a very cool, Ritz is actually a really cool example. This is also available in my GitHub repository. I won't do it justice. You really should look at the code, but I'll give you the gist of what it's doing, and I'll show you how it implements the function interface. This essentially defines a map, which is a concurrent hash map, that's going to act as a cache of the results of prime number computations or calculations. So you're probably familiar, computing prime numbers is fairly processor intensive. So if for some reason you needed to compute a lot of prime numbers or check to see if a number was prime or not, and you had to do this a lot, it might actually be a win to stick the results of checking if a number is prime into a hash map, in this case a concurrent hash map, so that you wouldn't have to redo that expensive computation every time, but you could just look it up and see what its previous value was. This could be useful if you're doing some kind of cryptography, some kind of key analysis. All right, so what we're going to do here is we're going to use a really cool method on concurrent hash map called compute if absent. And this implements something called atomic check then act semantics. And you can read this paper here if you want to learn a bit more about check then act and why check then act is very problematic if it's not atomic. It's a little beyond the scope of this discussion to give you the nitty-gritty on that, but I'll kind of walk through it as we talk about it. So this particular method, compute if absent, is an atomic check then act method. And let me explain how it works. So the first thing to remember is this is a concurrent hash map, which means it can be used in multiple threads. And just for sake of argument, if you go back and look at this program, you'll see what it does is it spawns a pool of threads, and then it goes through and it uses the pool of threads, which on a multi-core machine will be mapped to a bunch of different cores, so it can run in parallel. It'll go and check a bunch of numbers to see if they're prime or not, and it'll do it all in parallel. So what we're going to do here is we're going to have a variable called smallest factor, which is going to give back the results of compute if absent. And we're going to pass in a number that might be a prime. We don't know yet if it's prime. And the way this works is as follows. If the number that we're checking for primality, and let's say that this is the code to do that. This is a prime checker function that can check to see if something is prime. If we already know the answer, then compute if absent will simply return it. So if we already know the result, if there's already a value associated with this key, so in this case, the prime candidate is the value that's passed in here. If a number if we already know what its value is, we know whether it's prime or not, then we just return that. That's the easy case. However, if we haven't already checked that a number is prime, then we have to go ahead and compute it and store it in the map so that the next time we check, it'll already have the value. Okay, so far so good. This is easy if you have a single-threaded solution. But if you have multiple threads that are simultaneously trying to check the primality of a bunch of numbers, then we've got to be really careful. Because we don't want a situation where two threads, let's say that we have 30 cores or 32 cores, and thousands of numbers we're checking. We would like to avoid the situation where two of those threads, without loss of generality, both go to check to see if a certain number is prime. And let's say, for sake of argument, it's not been checked already. In that case, what we don't want to have happen is we don't want to have two threads simultaneously compute the value of the same prime candidate and then have to store the results into the map. That's wasteful. We just want one of those threads to do it. And what compute if absent does is it'll atomically check something, and it'll prevent anybody else from doing the same check on the same key while the computation is taking place. And the computation that's taking place here is to call the prime checker function with the key, which corresponds to the prime candidate, whose value we don't know yet. So this piece of code here, which is a lambda expression, will be run in only one thread of control in such a way that there's no race conditions and there's no additional computation taking place. And so this is a lambda expression that calls a function. That's the function. And we can also pass in a method reference if we want to. So this would be the way to write it as a lambda expression. Here's the same code written as a method reference. And as I mentioned before, your IDE will automatically let you go back and forth between those two representations. For my money, I find the method references a little easier to understand because there's just less syntax that's distracting. So that's what's going to happen. This code here will only run one time, and it'll run when we find a prime candidate that has not yet been determined to have its primality checked, pre-checked, or previously checked. Okay, so that's basically what's going on. This compute if absent method does all these magic cool things. Here is how compute if absent works. Now I'm abstracting here quite a bit because there's a lot of really cool stuff here that I'm not going to show you having to do with the way in which the concurrency control and synchronization is taking place. It's really, really neat. I'm just focusing on the Java 8 features here. So compute if absent is part of concurrent hash map. It takes a key and a mapping function, right? So you can see function is going to take a parameter, which is the parameter to the function, and a return value. And once again, this has to either be k or a subclass of k, and this has to be either v or a subclass of v. That's what you have to pass in there. So if you think what we're passing in here, we're passing in integer to integer, and this is integer, and this is a function that maps integer to integer. So look at the signature for prime checker. Takes an integer, returns an integer. That maps onto what's acceptable here as the function parameter passed to compute if absent. Okay, so far so good. There's a bunch of stuff that takes place. Basically what we're doing is it's going through every element in the map. No, I take it back. It's going to look up, it's going to go ahead and look up in the table to find whether or not we already have a value for this particular element. So it looks it up in the table. And if it doesn't find it, then it's going to go ahead and apply the mapping function. And again, this will all take place atomically. And as you can see here, prime check is the mapping function I'm passing in for my example. And the apply method is going to go ahead and compute the value here. It's going to go ahead and do prime checker call on the key and store the value in value. So that's what actually is being applied. That's kind of what the code expands to if you were to think about it being expanded. Obviously, it's not being expanded, it's just being called, but that's effectively what's happening here. Okay, any questions about that? Yeah? Good question. So if you recall Java, one of them has to do with the return values, and one of them has to do with the parameters. And so they're basically the same thing, they're just dealing with different types of things. Other questions about this example? Here's another example of a function. This is kind of another fun one. We're going to have a list of threads, and we're going to go ahead and have 3 threads, each of which we give a name. So we're going to have 3 threads, Larry, Curly, and Mo. And then what we're going to do is we're going to print them out in whatever order they were assigned initially, and then we're going to sort them, and then we'll print them out in sorted order. And this is EX5. So this is a pretty interesting example. We're going to call the sort method, and we're going to use something called comparator.comparing. I'll talk about that in a second. And what this kind of adapter function is going to do is it's going to take in a function. Sorry, this is a function. It's going to take a method reference that's going to be used to sort these methods by their name. So thread : get name is in fact a method defined on thread that can be used to compare the threads by some criteria. We could also do comparison by the thread ID if we wanted to. We could say thread : get ID instead of get name. That would be another method that would return the ID of the thread, which is probably some number like 574, versus the name, which in this case would be Larry or Curly or Mo. So this method uses the threadgetName method reference to impose a total ordering on some collection of objects, which in this case is going to be the list of the threads. All right, so let's take a look at this, and this will help you see how this works. So you can see here that we're going to have the comparator interface, which has a static method called comparing, right? That's what we're calling here. And the comparing method is going to take a function, which is going to be the key exchange or key comparator that we're going to use, which in this case is going to be getName. All right, so what it does here is this is the method that's passed the function parameter, which we call the parameter in the method is called, the formal parameter in the method is called key EX. That's just the name we give it so we can refer to it inside the comparing function, comparing method rather. And that's going to be thread : get name. And that's going to basically return the name of this thing. And these values here are the strings that are going to be compared to by sort. Remember, sort wants to pass, it wants to compare 2 strings, or 2 values, 2 parameters, which in this case will be strings, in order to see if they're equal, or less than, or greater than. And then what we do is we call key ex, which is this function, dot apply, and that's going to go ahead and basically compare to see whether these two things are, what the relationship is between the two strings that are part of this example. So what this turns into is c1.getName.compare to c2.getName. So the apply method is basically being replaced with the getName method. So that's how we can do the comparison. Now, the thing to remember about this stuff is the implementation details are a little bit gnarly, but the way it's used is really simple. So you just say threads.sort comparator.comparing, and then you pass in a function that can be used to get the values that you want to have here. OK, so that's another example of a function. Next example, and this will probably be the last one we'll talk about today, BiFunction. As the name suggests, a BiFunction is going to work on two parameters and return a result. So basically, you can see here that we have parameters t and u, which are the two parameters that are given to apply. And there's a parameter r, which is the result, which will be the result of applying a function to t and to u. So let's take a look at an example here. We're going to use our stooge map again, except this time we're going to do something a little different. What we're going to do now is we're going to show two different ways of subtracting some value, in this case 50 IQ points, from every element in the map. Let's say we put the stooges under some kind of IQ test and they turn out to be even stoogier than we thought. So we want to subtract some IQ points from their current values. So one way to do this would be to use a Java for each loop. So here we're going to say for each entry in the entry set of this map, for each entry, go ahead and take the value of the entry, subtract 50 from it, and update the value to be the new value that we just computed. So that's kind of the old school way of doing things. That's a way using Java 7 features. And we'll talk in a second about the pros and cons of that. It's pretty obvious one of the cons is it's verbose. Here is the BiFunction lambda Java 8 way of doing this. Same exact behavior, just way more concise. So we say IQ map, which is this guy, replace all. And what it does is it's going to allow you to give a lambda expression. And what we're saying here is subtract 50 points from each value and have the side effect of replacing the current value with the updated value. So really concise, way more concise than that code. This is basically saying for every element in the map, do this computation and update its value accordingly. Now, what's interesting about this, there's several things that are interesting about this. Not only is this more concise, right? So this code is just more verbose. This code is more concise. There's also another cool property of this code. This code is atomic. So replace all says, do all of these operations in the map in such a way that the map's internal state is not corrupted. Whereas if you were to do this code in multiple threads, is not corrupted when called from multiple threads simultaneously. If you were to call this code from multiple threads, chaos and sanity would break out because you'd be doing reads and writes on values that were not protected by locks. And that would lead to race conditions and memory visibility problems and other kinds of concurrency hazards. Whereas this code, because it's all hidden behind the replace all single entry point into that concurrent hash map, can take advantage of how things work under the hood to do that atomically. If you'd like some more information about how this works, take a look at the link here at the bottom, which talks about the concurrent hash map atomic operations, including replace all. There's a bunch of atomic operations, replace all being one of them. OK, so that's what we're trying to do at a high level. Let's now take a look and see how replace all is defined. Replace all takes a BiFunction. And so as you can see here, it's going to have these two parameters, which are k and v. And then it's also going to have a return result. And what it's going to do is it's going to take that function and it's going to go through every element in the map and it's going to apply that function to each element. So you can see here it's going to do the function.apply with the key, the old value, and it's going to update the new value, and it's going to replace the old value with the new value. And naturally, it does this all atomically. I'm not showing you the atomic part here. It's a little beyond the scope of the discussion, but just showing you that how the Java 8 code is used. So here's the lambda expression that gets passed in to this replace all method as a function. Here is when apply gets called, what it's doing, it's basically taking old value and it's subtracting 50 and it's updating new value. That's the side effect or the effect it has. And that's basically how that method works. And what's so cool about it, as I mentioned before, is not only is it really concise, but it's also atomic, or at least maybe a better way to say it, thread safe. There's some subtle differences between atomicity and thread safety, but it's thread safe. It won't leave, you will not end up with the map in inconsistent state if multiple threads call it simultaneously. Okay, any questions about that? I think we do have time for one more of these things. We'll do supplier. A supplier is an interface that returns a value but takes no parameters. So you can think of a supplier as something that is a producer. It's producing something. And the single method it has is called get, and it returns something of type T. Now, this is a particularly interesting capability, and it's actually a little bit confusing because oftentimes you can, in fact, pass parameters. They just aren't passed through your parameter list because there is no parameter list. But you can use some other magic, taking advantage of other things we talked about, like effectively final variables. So here's an example that we'll look at in much more detail way, way later in the course, probably like November, but I'm just giving you the foreshadowing here to talk about suppliers. And it's in my EX8 folder. What this is doing is it's a program that's going to asynchronously compute the multiplication of two big fractions. So a big fraction is a class that I've got in this example where you can give it big fractions and it'll go and do arbitrary precision big fraction arithmetic. You can add them, you can divide them, you can subtract them, and so on and so forth. Honestly, don't know many uses of big fractions like this, but hey, I needed an example to illustrate the point. So what we're going to do here is we're going to go ahead and define a supplier lambda, which when run in a background thread in parallel to other stuff, will multiply two big fractions together. So here you can see we take string f1, which is one big fraction string, string f2, which is a second big fraction string. We create big fractions from those strings, and then we multiply bf1 by bf2. So big fraction arithmetic, which is actually fairly computationally intensive if the fractions are big enough. And then when we're all done, we're going to wait for the results. I'm not going to talk about that here. I'm just going to focus on the supplier lambda. That's what's called the supplier lambda. Notice how we can actually pass parameters into this lambda, even though get doesn't formally take any parameters. And that's because we can pass them in as effectively final variables. Supply async is a factory method on completable future. We'll talk about this in great detail much later in the course. What it basically does is it takes this supplier lambda that's passed to it, and just like we do with lambdas, right? We create it, we're going to store it, we're going to pass it as a parameter, and then we're going to execute it later in another thread of control that resides in something called the common fork join pool. Don't worry too much about that at the moment. We'll cover it later. If you were to look at the implementation of supply async from the completable futures class, here's what it would do. It would take a supplier as a parameter, and in this case, it's going to take that supplier lambda we just looked at that had the initialization of the big fractions and the multiplication. It'll take that, and then it's going to go ahead and make an internal object that's going to store that supplier. So we're going to pass this thing in as a parameter. We're going to store it in another object, and we're going to tell that fork join common pool, this fork join pool common pool, we're going to say, go ahead and queue this thing up, queue up this async supply object, which contains the supplier. Queue this thing up to run in some background thread in the pool when there's a free core, a free thread that can compute it. So it's just kind of queuing it up. So that's a great example of what I talked about before about a lambda, right? You can store it, you can pass it. In this case, we're passing it and we're storing it, and then we're going to execute it in a different context, in a different thread, in a pool of threads. Again, under the hood, if we were to look at the async supply method, It's got an exec method, which is going to be called when the time is right in a background thread. And what that'll do is it'll say fn, which is the supplier that was passed to it here. It's going to take that supplier lambda, and it's going to go ahead and say fn.get. And when that call is made, it's going to go ahead and do the computation. So this computation is going to run in a background thread, in a pool, to do that multiplication of the two big fractions, or whatever, right? That's just the example I used. But more generally, this code is going to run that computation in the background. And what's cool about that is this code here doesn't really know the details of what that lambda expression is, but it simply stores it in a variable that's passed around through some queues and then finally run in a totally different thread of control. So that's one example of the concept of a supplier. Here's another example of the concept of a supplier. This is one that uses something called optional, and you can find that in the EX6 code. So optional is I'll talk about what optional is in a second. It's a new Java 8 class that helps you get rid of the need to check for null pointer references or null references in Java. We're going to have a map called the being map that associates beings like demons or angels or whatever with their personality traits. So a demon is naughty, an angel is nice. Then we have a container called an optional, which might or might not have a non-null value. So that's the cool thing about optionals. They keep track of whether something's null, so you don't have to do null checks anymore in your code. So we stick something into this optional using whatever being name the person typed in. We don't know whether they put demon or angel or anything, so it might actually not be a being we know anything about. And so what we want to do then is we want to print the results. And if there's actually a real mapping here, and if we really do have a disposition, naughty or nice, because we gave a being that the map already knew about, in that case, it's going to go ahead and print the result. However, if we gave it a being that we don't know anything about, then what it's going to do is it's going to go ahead and run the lambda expression that we give here, which is just going to say, I don't know what this thing is. It's unknown. And so unknown is the thing you pass in if there's a null entry in this optional. So you never have to check for null. You just give the code that you want to run if something doesn't have a value. In other words, if it's null. And the way it works under the hood, here's what or else get does. It takes a supplier, and as you can see here, it'll take this as the lambda expression, just the string unknown. And if there is already a value, the value gets returned. Otherwise, we return whatever this thing gives us when get is called. So it's a supplier. The get method returns its value, which in this case is unknown.